you for the kind invitation. I'm very sorry for not being physically there. I very much hoped if I could, but there were some uncertainties involving trip to moving from Japan to the UK and isolation, all this nonsense. So I'm sorry about that, but I hope I could celebrate Hubert's birthday. I mean, 70 years birthday or 8 years birthday in person, hopefully in the future. But it's still great that I can talk about my ongoing project with Benjamin and Tomohiro Sakamoto, which is about macroscopic fluctuation theory for integrable systems. So this theory of, macroscopic fluctuation theory it's a universal tool, essentially, to study large deviation properties in many-body systems. And it has been primarily developed for classical diffusive many-body systems. But the idea per se seems to be rather universal, so that's what motivated us to try to generalize the realm of macroscopic fluctuation theory, MFT, to incorporate the effect of ballistic transport. And it turns out that some very nice properties of integrable systems do facilitate such generalization. Okay, so, oops. I thought I could switch to the next slide by a single click, but I don't. Anyways, are you seeing the full screen or? Okay, I think I know what to do. Enter full screen. That should be fine.
Yeah, that's better.
Yeah, but then okay, perfect. So before going to the theoretical aspect of it, I just wanted to quickly mention that large deviation, or full counting statistics, if you wish, has been studied experimentally in several contexts, like electron transport using some mesoscopic devices, or even more recently, people started studying full counting statistics using ultra-cold atoms. For example, in this very recent experiment, people studied the full counting statistics of spin transport in the isotopic XXD spin chain using a bunch of bosonic rubidium atoms trapped in an optical lattice. And what was surprising for me was that they could really take a snapshot of at each time instance of the entire sample, so that they could really obtain the probability distribution of the spin transport. And from that, they could, for example, see that the fluctuation of this spin transport is governed by Gaussian orthogonal ensemble, so some random matrix process for some initial conditions. So what I want to say here is that you can really learn a great deal about transport by looking at full counting statistics of the system, and you can also study it experimentally. But I would say here that a versatile tool to study full counting statistics in quantum many-body systems is highly desired, and in particular for integrable systems, because we can do a lot of manipulation, also they can be experimentally realized. All right. So to understand how MFT works, you have to also first remember what the large deviation theory is. I think this isn't really necessary, but just to make sure. So in the classical case, at least, one is primarily concerned with the rate fluctuation of some fluctuating quantity AD that is extensive in T. So this is a parameter, and I'm going to choose it as time, because I'm considering the large deviation in transport. And this quantity, fluctuating quantity AT, could be actually anything so long as they are extensive, but I'm going to choose the time integrated current for AT. And this time integrated current can be written also in this way. And what large deviation theory tells us that for large T, this probability of finding some profile J should go like this, which is exponentially decaying in T with coefficient being given by the large deviation function. And this should, of course, take its minimum value because that's the most probable situation. But in practice, it's not that easy to directly work with this large deviation function. So what people do instead is to define the scaled cumulative rating function in this way, which is valid for large T. And this scaled cumulative rating function is related to the large deviation function via the Legendre transformation in this way. So what I'm going to do is try to calculate this f of lambda or some associated cumulants. Right. Now in the quantum case, JT, this integrated current, is actually not a very natural observable because it's integrated over time. But you can still write down the same probability considered in the classical case, for example, by considering the probability of measuring the total charge Q0 at time 0 and Qt at time t in the right half of the system. So this means, so this the difference of the Qt and Q0 is precisely the amount of the total transfer charges during the time t, and this probability is of measuring them is precisely the same one as before. In any case, you can have f of lambda either in classical or quantum, and but directly computing f of lambda could be always challenging. So what people do instead is to try to at least calculate some lower cumulants. So cumulants are defined in this way, and for example, this current is, this is trivial. The C1 is always trivial, but C2 is, for example, given in this way, which is variance and also called the register rate. Let me just point out that there are really a number of important results in the study of full counting statistics in quantum many-body systems. For example, as both of you probably already know, there is a celebrated Davidoff-Letopic formula, which provides an exact scaled cumulative rating function for charge transport in free fragments. So this is obviously important result, but you might say it's not that realistic because it's not interacting. But somewhat surprisingly, you can also obtain exact results in full counting statistics, even in interacting systems like integrable quantum imperative systems. And these models were intensively investigated by Hubert and Paul and other important people. And there are really a series of beautiful works, and which I think is really surprising because these are supposedly very complicated models. And you can also obtain the exact full counting statistical, f of lambda scaled cumulative function for example, conformal field theories, both in 2 dimensions and higher dimensions, and also in integrable systems. So what I'm going to do today is not really give you some new results. Of course, you might also obtain some new results by pushing our formalism further, but rather try to reproduce some of the results obtained by this paper by Benjamin and his colleagues. But I think this is meaningful because MFT has served as a very universal framework and applied to many important models, and now you can put this integral system, whole class of integral systems into that models that have been dealt with by macroscopic fluctuation theory. Okay, so now what this macroscopic fluctuation theory is telling us about is that only inputs needed for this theory to work is some hydrodynamic quantities like transport coefficients, and it has been primarily developed for diffusive systems. So what does it say? So it starts with probability of observing a hydrodynamic density and current profile in these guys during a time, hydrodynamically large time t. And then in infinite volume, this MFT is telling us that probability distribution should be given in this way, where this diffusive current, JDiff, is given by fixed law, obviously, because this is diffusive. And sigma rho is mobility. So you might think this is not so intuitively clear. So I'm going to provide you one justification. But before doing that, let me use this probability distribution, so the assertion from MFT, to write down the scaled cumulative rating function. So this is given by the path integral formula over rho 1j. And if the initial condition is fluctuating, you also have to put this probability of finding the initial density profile. And because this theory is basically built on hydrodynamics, we have to also put the continuity equation in order to enforce this the fact that this hydrodynamic continuity equation is satisfied at each space and time. Finally, you also have to put probability of finding such a density and current profile. And formally, at least, this formula is supposed to be correct. But apparently, this is quite a monstrous expression, and one doesn't really know what to do with this. So you have to massage it a bit. Now, before doing that, I have to know how to write down this probability of finding the initial density profile, which actually can be done pretty easily using some statistical mechanical idea. I didn't write down the derivation of it, and I think we should take it as a given. And for later use, I'm rewriting it in terms of entropy density, free energy density, and also beta of x, which is defined in this way. So now we have this initial probability of finding this initial density profile. And now, how do we justify this MFT assertion for this probability distribution? One way of doing that is to invoke fluctuating hydrodynamics. So fluctuating hydrodynamics says that on the mesoscopic scale, Navier-Stokes equation itself isn't really enough, and you have to incorporate the effect of fluctuation by putting white noise in the equation. And this in turn promotes the original equation into the Langevin equation. And you might ask, well, then where does this white noise come from? Well, one way of thinking is it's coming from the high energy degrees of freedom that is being integrated out or washed out when writing down the hydrodynamic equation. So these high energy degrees of freedom are supposedly not playing any role because hydrodynamics is supposedly for low energy dynamics, but they are still important and accounting for the fluctuation coming from the interaction between the macroscopic degrees of freedom protected by the conservation laws and the microscopic degrees of freedom that are ignored in doing hydrodynamics. So fluctuating hydrodynamics is a kind of neat way of incorporating the effect of microscopic degrees of freedom by just putting white noise. And as far as fluctuation is concerned, this should be, people at least believe that this is the right thing to do. Once you believe in fluctuating hydrodynamics, one can rewrite scaled cumulative function in this way, which I think is physically intuitively clear than the previous expression. Now what you have to do is integrate an overall path integral and take averaging over the noise. So this noise is now accounting for the fluctuation stemming from the dynamics, not initial condition, but the dynamics. And this is actually also analytically amenable. So I'm going to take this as our starting point of doing MFT for integrable systems. Okay. Now I have to turn to ballistic transport. So previously, just to reiterate, it was all about diffusive transport. So the scaling we are talking about are different. In this case, for example, you can consider hydrodynamic equation for the tail step. So tail step is some stochastic exclusion process on the line. And its hydrodynamics is given by Poiseuille's equation. Very simple in this way. Now the point is there's no second derivative of density with respect to x, and instead you have some current that is not linear in rho. It's non-linear in general, and that causes some problem. But in any case, we can carry on, and because now this relevant scale is Euler scale, which is x and t being very large, and they are of the same order, the effect of fluctuation is actually coming only from the initial condition. Why? Because the fluctuation accounted for by this noise is actually subleading. It is going to scale like square root of t, and they are subleading in this scale. So you can safely ignore them, and this is the MFT for the ballistic transport. I'm not going to say this is really proved, but I would say this is a sensible generalization from this case, the diffusive case, to the ballistic case by ignoring the noise coming from dynamics, which is subleading. Now you can try to do a bit more by exponentiating this delta function. And in doing so, you have to introduce an auxiliary variable h. And now this MFT action is it's rather easy to see that they will grow linear in t for large time, which means that for large t at least, the only dominant contribution coming from this path integral is from the saddle point of this MFT action. So the problem now boils down to the optimization of the action. And if you successfully do that, you can calculate this scaled cumulative function. But of course, that's not that easy to do. And I mean, if you do optimization of this action, you end up with this bunch of equations with non-trivial initial conditions. And the situation is not that good because if you know a bit about hyperbolic systems, you'd easily imagine that this dynamical equation is going to inevitably face some singular behavior, which is a shock. And this is not welcoming news. And on top of that, you don't really have a guiding principle to single out a proper physical solution of this equation, because in the hydrodynamic case, you have some conditions like flux conditions or entropy conditions that you can use to single out a physically sensible solution of the hydrodynamic equation, but you cannot do it here. So it's not like we are stuck, but things are quite different. But in the case of integrable systems, at least, it turns out that we can really do a lot more primarily because there's no shock in integrable systems. The fluid profile is always smooth. And that's what makes IPhT for GHD, I mean, integrable systems, really doable and accessible. Okay. Yeah, I'm going to just skip this. I think I'm going to run out of this time. But to do MFT for integrable systems, of course, I have to talk about generalized hydrodynamics, because only input needed for MFT is the hydrodynamics of the system. So if you know the hydrodynamics of the system, you can do MFT as well. That's the idea. So, but I think nobody has talked about GHD before, so let me just explain a very important, and I think this is the only important idea that you have to bear in mind, is that on the hydrodynamic scale, quasi particles in integrable systems behave pretty much like tracer particles of hard rods. So hard rods are, of course, some bunch of rigid objects on the line colliding elastically, and you can try to trace the trajectories of each rod by putting tracer particles in each rod. For example, in this magenta line, so one of the trajectory of the tracer particle is depicted. Upon each collision, it's just tracer particle hops to another rod and carries on with the previous velocity. And this is quite surprisingly quite true to many other integrable systems, no matter how complicated they are. I mean, of course, this jump distance upon each collision could be velocity dependent, and there are some complications that are incurred by some non-trivial interaction, but in general, this picture is quite robust. And that's why GHD is so universally applicable to integrable systems, so long as they are bed solvable. Okay, so now GHD equation, of course, that's the idea, important idea, but of course you have to put idea into the equation. And this is the GHD equation, which simply tells us that on hydrodynamic scale, root density or density of particles are transported according to this very simple equation, with the effective velocity being the functional of rho. But this isn't actually very convenient for my purpose. So I have to introduce new set of fluid variables, which are given in this way. where C is the susceptibility matrix and A is some matrix called flux Jacobian, defined in this way. So this beta can now be used to obtain yet another way of writing down GHD equation, which is in terms of normal mode. So normal mode could be really, there are basically infinite number of ways of defining normal modes because they can be normal modes so long as they are convectively transported in this way. But I'm going to use one particular normal mode, which is the pseudo energy for our purpose. Pseudo energy is a kind of quasi-particle energy with some non-trivial effect of interaction, but the precise definition of it isn't important here, so I didn't write it down. You can get this epsilon from beta according to this transformation rule, where R diagonalizes the effective velocities. Sorry, the Jacobian matrix and the eigenvalues being effective velocities. Okay. How much do I have time actually? Perhaps
I think you should have 35 minutes plus 5 for questions. So I think
yeah.
you still have like 6 minutes plus 5 for questions.
Okay,
so
great.
you're
Thank
all right.
you very much. Yeah. Then I should probably skip this. So one of the important inputs for MFT to work for integrable system is that you have to know how to solve a GHD equation. And of course, it's not exactly solvable literally, but there is a way of obtaining exact, solving the initial value problems in GHD by using the method of the characteristics. So this is the same old thing that has been intensively used in, the hyperbolic systems and other contexts. And the way it works is pretty similar to that usual conventional method of characteristics. So you have to define u of x and t in this way. So this rho is some density of some system, and is satisfying this kind of equation. And to know the solution of this equation, you have to know what kind of equation is satisfied by this u of x t. And once you know that, you can use this by plugging u of x and t into the initial value of this rho. And the problem is now boiling down to the determination of u of x and t, which is satisfying this kind of equation coming from the method of characteristics. And you can do exactly the same thing in integrable systems, GHD, at the price of having additional parameter, which is theta. But the underlying idea is really the same. So I'm going to skip all this derivation because you don't really need it. Only thing I want you to remember is that I define u theta of xt in this way, so that once you know it, you can plug that into the initial epsilon, and you recover the full profile of this epsilon theta. And the way to determine u theta of x and t is to solve this equation self-consistently. I didn't write down the k, the function k here is just coming from TV thermodynamic ansatz, so you can easily obtain them. You just need to solve this consistently, and then you can get the full profile of the epsilon. So finally now, MFT for GHD can be discussed. So I'm going to consider transport of a charge which isn't really physical. In the sense that they are not labeled by 1 or 2, it's not like energy or a number of particles, but they are labeled by theta. You can do it in infinite volume because these q theta labeled by causal momentum still constitute a complete set of charges. They are local. And this is just for a technical reason. And once you have cumulant, all these things for this charge, you can recover easily those for physical charges as well. So this is the MFT equation you have to deal with. And as I said before, you have to optimize MFT equations in order to compute cumulants and generating function. This is the consequence of the optimization. And this is actually useful. So you have to transform into the equation in terms of normal modes. I defined normal mode according to this rule before. And now you have to know how you can also sensibly define normal mode associated to new variable h here. Remember that this h appeared as a consequence of the exponentiating the delta function in the original path integral formalism. So motivated by how we can obtain epsilon from beta, I suggest to define G in this way. And actually we can do it because there is a nice compatibility condition like this, which guarantees that there is such G can indeed exist. So if you do that, you end up with this kind of new set of MFT equations. Now the question is, how does this epsilon vary as lambda changes? And this is important to know because that information is needed to compute cumulant quantities. I'm not gonna write down the derivation because that's a bit involved, but at the end of the day, you get this equation for the derivative of epsilon. And okay, R I didn't define. R is another solution of the method of characteristics, so it's pretty much like E of theta. And you shall have this. And once you have this kind of equation for the epsilon, you can calculate cumulants. Let me go quickly from here because it's just computations, but I want to emphasize that, for example, you can compute C3, so third cumulant, using these equations. And surprisingly, this precisely coincides with the C3 obtained by Benjamin and his colleagues' work. And this is not that straightforward, as you can see from the expression, but this is actually precisely what was obtained before. So I think this is quite a nice sanity check. And of course, in principle, one can compute higher cumulants too. And for physical charges, you can just replace R inverse T with some dressed quantity. I didn't define dressing operation. It's just a way of incorporating the interaction. You might wonder if these are really correct, but it actually, the validity of these results were confirmed against the hydrodynamics before, and agreement is quite precise, I would say. These are scaled energy. I mean, the cumulants for the scaled energy, and these are really agreeing pretty well. Now, finally, I want to talk about what this epsilon is really about. I mean, I said at the beginning that this isn't really hydrodynamics. This epsilon is satisfying some kind of dynamics coming from MFT consideration. And morally speaking, this is accounting for, this dynamics is one particular representative dynamics that is contributing to create some rare fluctuations. So of course, in principle, there are loads of dynamics that do contribute to rare fluctuations, but the beauty of the MFT is that you don't have to deal with all these bunch of dynamics, but you can just single out one of them. And this selected dynamics with non-trivial boundary conditions is going to give you the dominant rare fluctuation. And to understand what this epsilon is all about, I think it's illuminating to remember how in this work by Benjamin and other people, how they studied large deviation in integrable systems using another different way, which they call the ballistic fluctuation theory. So this is another way of studying it by biasing the state instead of dynamics. So in the MFT, what you do is biasing the dynamics, but in here, they biased the state. And you might wonder, why ever do you want to do this kind of thing? But actually, this is nice because it turns out that this lambda derivative of the scaled cumulative function is given by simply this biased state by plugging J in here. And furthermore, this biased measure turns out to be homogeneous, stationary, and clustering, which means that you can now sensibly define a set of new beta dependent on lambda in this way, so that with respect to this new measure, you can have this kind of it's essentially a new state. And this also in turn induces a flow of beta, which means that you can write down the differential equation for the beta, describing how beta evolves as lambda varies. You can also write down the same thing for the epsilon, which reads like this. So I want to ask a question. What can we identify epsilon with epsilon 0 and t? So epsilon lambda is coming from BFT, not MFT. And this epsilon 0 and t is coming from MFT. Okay. Now, to answer this question, I have to show you that at x equals 0, MFT dynamics is stationary, quite surprisingly. Which means that if you take a time derivative at x equals 0, we have 0, except at two boundaries. You can forget about these two boundaries. They could be tricky in some situations, but in our case, you can ignore them. This means that at x equals 0, you can define a set of Lagrange multipliers, beta, theta, lambda, in this way. And you can also show that within MFT, not the BFT, I think this can be confusing, but just to emphasize it, within MFT, scaled non-generating function can also be shown to be given by this way. It means that now you can really identify epsilon theta of 0 and t and epsilon. Oops. Can I go back? Yeah, this guy. And this is quite great because now you can put BFT in the context of MFT, meaning that MFT dynamics is in principle not homogeneous, non-trivial, but at x equals 0, some non-trivial stationary dynamics is taking place, and that is described by the BFT, plastic fluctuation theory that was formulated by Benjamin and his colleagues. So I would say there is some nice connection between these theories. And but of course there are still things to understand, like for example, why then we don't need to know the profiles of other places in space-time, like not x equals 0, like x equals 1 or 2, whatever. For some reason it seems we don't need them, but we have to understand this, and we don't really have an answer to it yet. Anyways, okay. Clearly, I'm running out of time, so I'm just going to skip fluctuation theorem. This is just to say that I can derive fluctuation theorem within the framework of ballistic MFT also, without invoking integrability. So I think this is nice, but I don't have time. So just to say that finally, as a concluding remark, that MFT for GT is just one way of generalizing MFT, but it seems to work very nicely. And there are still challenges we have to tackle, like incorporating the Carlton fluctuation. For example, if you start with the initial domain wall condition, I don't think MFT works, at least in the current form. So you have to somehow generalize it. And of course, it'd be nice to relate that our findings with the previously obtained results in the context of integrable imperative systems by Hubert and others, and that'd be really nice. And finally, happy birthday, Hubert, and thank you everyone for listening.
Thanks a lot. Thanks a lot, Takato, for the nice talk. Are there any questions for the audience present here or online, maybe? Nothing? Maybe I have a little one. So it's something, maybe a little bit tangential to what you said, but when I saw your set of equations, you have this set of complicated, I think, 4 equations that you have to solve in there. You talk about the method of, like this, for example. So you talked about the method of characteristics as a way to solve these sorts of problems. So is that sufficient to solve this as well? Or have you tried to do any sort of numerics to to implement these equations to find solutions?
Yeah, of course, eventually you have to use numerics to really see the exact profile. But what I'm saying is that once you have equations in this way, I mean, in terms of normal modes, you can use the method of characteristics, like
Yeah.
as I wrote, here, like epsilon, these guys, and u theta, so that now problem boils down to the determination of u theta.
Yes.
In this way, and when you solve this, of course, you have to numerically do it, but yeah, that's always the case in integral systems, like solving TV equations and all this.
Yeah, I mean, I guess what I was saying is that these equations that you get, they seem so complicated. I was wondering if this was still enough characteristics, or if you needed somehow something more complicated.
No, not really. Yeah, the complication is coming from the boundary conditions, I would say. And yeah, but you can incorporate it nicely. And as far as calculating cumulants in the homogeneous case are concerned, you can do it analytically, actually. You don't have to do numerics.
Oh, okay, that's great. Okay, thank you. Any other questions? It seems not, so thanks again, and hope to see you in person soon.
Yeah.
Bye.
Yes, thank you.